Hey everyone, so this is just going to be a video on the conservation of momentum and introduction to collisions. So we're going to learn a little bit more about what the conservation of momentum is. We talked about it a little bit when we were going over the guided reading, but now we're going to learn about what it is, how it's applied, and how we use the conservation of momentum to work with collisions. So we're going to learn about two different collisions today, inelastic and elastic. So let's get started. So conservation of momentum, this is just the law of conservation of momentum definition, but there is also an equation that is a little bit easier to read. So we'll go over this law and then talk about the equation. So the law of conservation of momentum states that in the absence of external forces, so all of your forces that are happening inside of your system are within the system. It's not happening anything external. So in the absence of external forces, the momentum of the system remains unchanged. And a good example of this is the cannon and the cannonball. So we talked about it when we were going over Newton's third law, that for every action, there's an equal and opposite reaction. So the force that is shooting off the cannonball is the exact same amount of force that is shooting and recoiling the cannon. It's just acting in opposite directions. Okay, and so that force is all internal to your system. All right, there's no external forces going on there. So this is a great example because the momentum that you are starting out with, your initial momentum, is equal to your final momentum. Okay, so the momentum after you fire the cannon. And this is all due to the conservation of momentum because your forces are all internal to your system. There's no external forces here. The momentum that you start with is what you're going to end with. All right, so the law of conservation of momentum describes the momentum of a system. If the system undergoes changes wherein all the forces are internal, just like our cannon and cannonball, the net momentum of the system before and after the event is the same. And again, that's the net momentum. So you could have different objects within the system, like let's say the cannon and the cannonball, right? They're both two different objects, but because we're counting them in the same system, we have to solve for the net or the combination of the the momentums going on there, okay? I almost said forces, like we're still talking about Newton's stuff, but that's okay. So another examples of this are atomic nuclei in undergoing radioactive decay. Again, that's kind of big. We're going to be talking about that way in the future from now. Car collisions and stars exploding. Okay, so this is when all of your forces are internal to your system. And again, your system can contain different objects, just like our cannon and cannonball, but the forces are all internal to your system there. All right, so this kind of goes back to Newton's second law. All right, so Newton's second law states that if no net force is exerted on a system, then no acceleration occurs. All right, so if all of your forces acting on your system are balanced, then no acceleration is going to occur. So if no acceleration is occurring, then there is no change in your momentum. I mean, no change in your velocity, which means no change in your momentum. Kind of gave it away there, but that's all right. So again, this all leads us to say that P initial, and again, that's your momentum, is equal to P final. Or your total momentum that you start with is equal to your total momentum that you're going to end with. All right, and this is the conservation of momentum. This is the big picture equation of the conservation of momentum. That whatever momentum you start with, you're going to end with. Okay? So now let's talk about collisions. I hope you got this equation down. If you didn't, get it down. All right, so now let's talk about collisions. So our first collision that we are going to talk about is elastic collisions. And elastic collisions are when objects collide without being permanently deformed and without generating heat, and the collision is elastic collisions. All right, so I got two carts here. One cart, two carts. So this is going to be an example of elastic collisions. All right, so cart A is going to come in and hit and collide with cart B. And the momentum is going to transfer from cart A to cart B. So cart A is going to slam, they're going to collide, and cart B is going to move away with the exact same amount of velocity as cart A. Again, in case you missed it, this is an elastic collision. So there is no deforming of our objects. All that is happening is that the momentum is being transferred from one object to another object. All right, so collision and ending there. And we get our elastic collisions from the conservation of momentum. So whatever we start with, we need to end with. And let's just see what that looks like on the whiteboard. And don't freak out, this is going to be a kind of a scary equation here, but don't freak out. No one panic yet, okay? So to write down our conservation of momentum, we say that the change in P, or our initial, right? That momentum initial is equal to our momentum final. And we use this for our collisions. So this is going to be elastic. This is going to be an example of elastic collisions. All right, so again, we have cart 1 that has a mass, and it's going to have a velocity. So in order to solve for its momentum, all we have to do is multiply it out. So we can say that cart 1 initial times its velocity 1 initial. And it's going to be in the same system as cart 2. Again, even though they're both different objects, they're going to be in the same system because we want to study their momentums. So if we combine them in the same system and we look at the collision, right? So cart 1 initial multiplied by the velocity 1. And now we have to add it to cart 2. So cart 2 initial times the velocity 2 initial. Okay, so this is all happening before the collision. So what this equals sign represents is that collision point. All right, so I'll write down collision. I hope I'm spelling it right. You all know that I'm a terrible speller. But that is the point where the collision is going to happen. So the point where these two things collide. And then what's going to happen is that cart 2, or whatever is hit, is going to be transferred through that momentum. And it's going to end with the same amount of velocity that cart 1 started with. So basically, this is all to say that the masses don't combine and they walk away with the different velocities. They don't all walk away with the same velocity. So basically, cart 1 final times the velocity 1 final plus cart 2 final times the velocity 2 final. Okay, so again, cart 1 has a mass, it has a velocity. Cart 2, it has a mass, it has a velocity. So when they collide, they're both going to have a mass and a velocity. All right, so this is elastic collisions because nothing gets deformed here, right? Our carts are still fine. All that's happening is that the momentum is being transferred from one cart to another cart. All right, so another good example of this is with pool balls, okay? Or billiard balls. So when a moving billiard ball collides head-on with a ball at rest, the first ball comes to rest and the second ball moves away with a velocity equal to the initial velocity of the first ball. Again, just like we saw with our carts, right? When one collides with the other one's going to walk away with the same amount of velocity that the cart 1 came in with. All right, and that is just because the momentum is transferred from one cart to the other cart. But we can have different elastic collisions. All right, so we can have one like we've been seeing throughout this process, where cart 1 is going to come in with a certain amount of velocity, it's going to collide, and then cart 2 is going to walk away with the same amount of velocity that cart 1 came in with. All right, but we can also have it that cart 1 and cart 2 are coming into the collision with a certain amount of velocity, they're going to collide, and they're both going to walk away with the same amount of velocity that they entered with, but just in the opposite direction. And then another part of collisions here is part C here, where one cart is going to come in with a large velocity, the other one is going to come in with a smaller velocity, and then what's going to happen after the collision is that these velocities are just going to transfer. So cart 1 is going to come in with a large velocity, it's going to hit cart 2, and then the other one's going to walk away. Okay, so basically, as we can see with the billiard balls there, the velocities just get transferred, and that's just because the momentum gets transferred. But it all stems from the conservation of momentum. Okay, so whatever momentum you start out with, Even if it's for two different objects with two different masses and two different velocities, you're going to end with. And this is about the products of those things. It doesn't mean that you're going to end with the same amount of velocity and the same amount of mass, right? Because your velocities might change, just like we just saw, where one is going to get transferred to the other. But the products, or the net of these momentums, is going to be the same, okay? And if that doesn't make sense, come and see me, all right? And we can do some more examples with that. So moving on to our next collision is inelastic collisions. So a collision in which the colliding objects become distorted and generate heat during a collision. And this is called an inelastic collision. And you're going to find that this is kind of funny to say because I always say and then it gets all confusing. But this is when your carts are actually going to come together. All right, they're actually going to combine and get distorted together. So again, if we start out with one cart at rest, the other one is coming into the collision with a certain amount of velocity, what's going to happen is that our carts are going to get distorted or stuck together, and then they're both going to move away with a certain amount of velocity. Okay, so basically our masses combine. And this kind of goes back to the distorted part. Our masses combine. But this collision, this inelastic collision, still follows the conservation of momentum. Why? Because our objects, they're still within the same system, and all of the forces are still internal to our system. So if we were to write out our equation for inelastic collisions, it would look something like this. So again, this is inelastic. And again, just like we saw, sorry about that noise, but just like we saw, these carts are both starting the same way, right? They both have mass, they both have a certain amount of velocity. So they're both going to start the exact same way before the collision. So M1 initial times V1 initial plus your M2 initial times your V2 initial. Again, they're both starting the exact same way. And that equal sign still represents our collision point. Still represents that collision point. So what's going to happen after this collision, like we saw with our carts, the masses are going to combine. So we need to find the product of our masses. So we're going to take M1 plus M2. And just like we saw with our two carts, right, they're going to combine and walk away with a certain amount of velocity together. So let's just call that velocity final. All right, so this is inelastic collisions. So this is when things get distorted and there is heat involved. This is an inelastic collision, okay, because they come together, things get distorted, and the masses get combined. All right, so let's look at some more examples with how we can kind of see this in real life. So an inelastic collision between two freight cars. So this is kind of like the train cars where they have that locking mechanism, right? And the masses are kind of combined there. So this is an example of an inelastic collision, okay? And feel free to do this out. I'm kind of running out of time, so I'm not going to do this out, but feel free to do this out. Work with this equation. One thing that I do want to go over is this one, because I think it's really helpful to get an idea of how these masses combine. So consider a 6 kilogram fish that swims toward and swallows a 2 kilogram fish that is at rest. If the larger fish swims at 1 meter per second, what is the velocity immediately after lunch? Well, the bigger fish, right? It goes, oh, the smaller fish, and then it eats it, right? So these masses combined, this would be the eating point would be the collision point, and the masses combined, and then the big fish walks away with a certain amount of velocity. Okay? So again, this is an example of inelastic collisions. This is where I'm going to end our presentation for today. I know that there's more involved here, but I'm going to talk about it more in class tomorrow. So after you watch this video, start working on the classwork. All right, the classwork is with Granny and Ambrose. If it seems confusing to you, send me an email and we can kind of walk through it together. And then once you finish that, finish the guided reading for collisions. All right, and that is your homework for tonight. I will see you all tomorrow. I hope you have a great day. Bye.